get back into some discussions with polygons in this first section. We're talking about things like triangles, quadrilaterals, octagons, nonagons, and decagons. The key here is that we're talking about the angles, focusing mainly on the interior angles of each polygon. So here you see we've got a little table set up where we've got polygon, the number of sides to each polygon, the number of triangles, I'll explain that here in a moment, and then how many degrees are inside that polygon. So in a triangle, obviously we know there are 3 sides. There's only one triangle inside of a triangle. And we know a triangle is 180 degrees. These other shapes we have here, quadrilateral, we've got a pentagon, looking at the hexagon. Quadrilateral, 4 sides. As you look at down here, I've got a rectangle drawn. But I'm able to draw a diagonal and cut that into 2 separate triangles. That tells you that I've got 180 degrees here, 180 degrees here, for a total of 360 degrees inside a quadrilateral. So 4 sides, 2 triangles, 360 degrees. In a pentagon, I can cut that into 3 triangles, which will give me a grand total of 180 plus 180 plus 180, or 540 degrees. With a hexagon, likewise I can do the same thing. Break that up into the number of triangles, multiply that number of triangles by 180, and it tells me that I've got 720 degrees inside of a hexagon. Alright, so the key thing here is that the number of triangles within a polygon is always 2 less than the number of sides. So that's why here in this column, you'll see it says n minus 2. The number of sides minus 2 will tell me how many triangles I have in that polygon, which will help me figure out the total of the interior angles in terms of degrees. So, what that helps us with is it kind of leads us into one of our theorems, which is the interior angle theorem for polygons. The sum of the interior angles of a convex polygon is equal to 180 times n minus 2. Again, that n is the number of sides of our polygon. So if we're talking about a quadrilateral, we'd have 4. If we're talking about an octagon, we'd have 8. So for example, find the sum of the interior angles of a convex dodecagon. And again, the key thing here is that these polygons have to be convex in order to use this formula. So don't forget, dodecagon, a dodecagon, that's a 12-sided figure. So I'd have 180 times 12 minus 2, which would become 180 times 10. So it tells me that there's 1800 degrees inside of a dodecagon. A second example, find the sum of the interior angles of a convex 16gon. Remember, once we get past 12 sides, we don't have specific names for those types of polygons, so we write down the number of sides and then just dash GON. So a 16gon. So again, since it's convex, we can use our same formula, 180 times n minus 2. So substitute in the 16, do the subtraction. 180 times 14 tells us that there are 2,520 degrees total for all the interior angles of that 16gon. So that tells you a little bit about the interior angles of a convex polygon, but what about the exterior angles of a convex polygon? So we do have something called the exterior angle sum theorem. Sum meaning total. If a polygon is convex, the sum of the exterior angles is always going to be 360. Now the key thing is this, that you can only have one exterior angle at each vertex. So for example, I've drawn a triangle down here, and it's actually an equilateral triangle, 60, 60, and 60. So coming off this vertex, you see one exterior angle. Coming off this vertex, you see one exterior angle. And again, down here, I just have one exterior angle coming off of that vertex. So, using my knowledge of linear pairs, I know that each of these exterior angles is going to be 120 degrees. So if I take 120 plus 120 and add on to it another 120 degrees, I see that my total is in fact the 360 degrees that my theorem says it should be. So how does this help me out? Well, if I want to find the measure of one interior angle and one exterior angle for a regular pentagon, okay, key term here, regular. Remember, for polygons regular, 1, it's got to be convex. 2, all the sides are congruent. And 3, all the angles will be congruent. So I know each interior angle will have the same exact measurement. So, in a pentagon, I know if I take 180 times 5 minus 2, I know that all of my interior angles add up to equal 540 degrees. So if the inside is 540 degrees, and I've got 5 angles because it's a pentagon, then I can take 540, divide that by 5. I know that each interior angle should be 108 degrees. Now, since it is a regular pentagon, all the inside angles are the same. That means that all the exterior angles will be the same as well. So, if I, again, use my knowledge of linear pairs, I should just be able to take 180 degrees, subtract 108, and find out that each exterior angle of my pentagon is going to be 72 degrees. So the nice thing is this, it kind of brings us to 2 conclusions. 1, if I've got a regular polygon, I can figure out the measure of one interior angle by taking 180 times n minus 2, and then just dividing that by the number of sides. The other nice thing it brings up is about my exterior angles. That to find an exterior angle of a regular polygon, I can take 360 and just divide by the number of sides. If it's a quadrilateral, meaning a square because it's got to be a regular polygon, then I know that each exterior angle is 90 degrees. If it's a regular hexagon, 6 sides, I know that each exterior angle will be 60 degrees. And so it's kind of a nice shortcut that we can use in terms of finding angle measurements of polygons, regular polygons. So I've left you with a couple of examples here at the end. We want to find the measure of each interior angle and each exterior angle for the following types of polygons. 1, a regular heptagon. Keeping here the fact that a heptagon has 7 sides. So again, interior angle, 180 times n minus 2 divided by n. So I substitute my 7 in. So I've got 180 times 5 divided by 7. That's not going to work out evenly. So I've rounded to the nearest 10th degree and get 128.6 for my interior angle. Subtract that from 180, and I know that my exterior angle should be 51.4 degrees. So secondly, a regular octagon. Again, at this point, if you want to try to do it on your own, hit pause real quick. You know it's a regular octagon, you've got your formulas, hit pause, and try that on your own. But again, octagon, 8 sides, substitute in. 8 minus 2 is 6, multiply that by the 180. So then I want to divide by 8 at the end. I get 135 degrees for my interior angle. To get the exterior angle, just subtract from 180 because they should be supplementary, and you come out with 45 degrees. In this last example, we're going to kind of switch it up a little bit. Again, it's still a regular polygon, in this case a regular dodecagon, 12 sides. But we want to find the exterior angle first. It gives us a chance to use a different formula. So for my exterior angle, if I take 360 divided by the number of sides, in this case 12, 360 divided by 12, I know that my exterior angle is 30 degrees. So now if I take that and subtract it from my 180, that lets me know that my interior angle should be 150 degrees. So that's the information on section 8.1, angles of polygons. If you missed something, just rewind the video and we'll be talking about the different types of problems tomorrow in class. See you then.